Okay, thanks everyone for coming to the Singular Learning Theory seminar. Today we're going to be hearing from Ash from the University of Waterloo, talking about inverse temperature in RLCT estimation. Take it away.
Yeah, nice to meet you, everybody. My name is Ashraf Ahmed. You could just call me Ash. So I am an alumni of the University of Waterloo. I graduated from my master's last year. Caleb actually here is a member of our reading group at the University of Waterloo. So for this work, over the past year, really, we have been kind of looking closely at SLT and trying to kind of see how can we make sense of the theory and most importantly, how can we apply it. So currently we're working on a communication paper for applied statistician. We're really trying to focus on how can we apply these tools in practice for typical problems statisticians would see. So kind of an infamous settings for singular model is obviously mixture models, which are extremely important in practice. Just kind of one small note about how statisticians see mixture models. So usually statisticians care about how much can they recognize or identify or estimate one of the mixing components from data. This can be typical in many situations. Like a prototypical example is if I'm doing cancer profiling and I'm getting data from a rare disease, and it's really hard to identify the mixing component. So people would usually run analyses to kind of try to measure things like prevalence and do we have a patient in the population and things like that. Now, this kind of motivated us by looking at three different regimes. So you see here what we call, or what's called regular. These are obviously well-separated mixing components. Regular in the normal sense of SLT. Singular, obviously, that's the SLT term. In this cases, we're using a mixing model, maybe two-component mixture model, but actually the two-data distribution is a single component. And our term here is what we call quasi-singular. And basically, this is cases, as you're going to see, something interesting happens when the mixing components becomes closer to each other in the parameter space. Now, the purpose of this talk is to kind of, or really the one of the main motivation of doing this work is to kind of try to see, okay, let's just apply SLT tools to some of the problems and see what happens. One important guiding question, because in applied statistics, as you can imagine, we work a lot with finite samples. So what really happens to asymptotic quantities like the inverse temperature? And that becomes a rather very interesting question. So I'm just going to start by setting the scene here. I have a few notation slides, so apologies for that. If there's anything not clear, maybe towards the end I could clarify it. But basically what we have here is a typical mixture situation. We have a mixture of Poissons. We can have as many mixing component as we need. You can see here that from the notation, I have K. Okay, so as you can see on the left-hand side, you have a typical triplet model. You have the parameter space big theta, var phi, that's the Breyer, and B, that's the likelihood function. And we have random variables that are distributed. We assume they're distributed according to some Poisson mixture. A typical example here is usually like an observational study where maybe an observationalist would sit in a park and basically try to kind of measure or identify the species of singing birds. So they would record the frequency of singing. So as you can see here on the right-hand side, this is obviously motivated by a real situation, but the data itself is simulated. So on the first column, this is the cases where you have a two mixture component data generating process. The mixing components have different rates. So you have different rates for mixture one versus mixture two. In the first row, the first rate is 15 and the second rate is 1, and the mixing weight is 0.75. And second column, this is the cases that we mentioned as quasi-singular, is basically the mixing component. As you can see from the data, they're quite fused. And you can see this because the rates are 10 and 5 versus 10, 15 and 15 and 1 on the left-hand side. Now, the other two columns on the right, these are actually truly singular. They're single component data generating processes. So the rates are either equal or the mixing weight is set to 1 or 0, which is what you would expect. Now, to kind of understand really what happens as we apply the tools, we're looking at three different regimes. We're looking at small samples. This is n equal 50, and we're looking at a typical sample that's 250, and a very large sample as you would expect from when the asymptotics kick in, that's 5,000. Now, the first thing I just wanted to show, just because there's going to be a few blots, is just to ground what's really going on. So as you can see here, this is basically the posterior samples from a two-component Poisson mixture, and basically the top row that's quote regular model if you ignore the isolated label switches here. And the bottom chart that's actually singular. So that's a single the digitizing process is a single component, but obviously we're using a mixture model. So you can clearly see the singularity. On the left-hand side, that's when you have a small sample regime. So you can see the posterior is a bit diffused around the singularity. And obviously, as we get more samples, you start to see that the singularity becomes a lot sharper and the posterior samples concentrate more. Hopefully this makes sense.
So do you mind if
Now,
I just clarify what's going on in this plot? So these axes are the mixing weights for the different Poisson mixtures, or the mean of the
So the XY axes, I would have pointed, but I couldn't point. But the
yeah,
XY
yeah,
axes, these are actually the rates for the Poisson components,
yeah,
and the Y axis, that's the weight, that's the mixing weight component. So
yeah.
what's really going on here because of the symmetry in the mixture, when you have a singular model like the bottom chart, you obviously have a singularity when one of the rate equal the truth, and obviously as you vary the weight as they go up from 0 to 1, the symmetry flips and you get the singularity in the other direction. So if you actually look from the top, you're going to see a normal crossing.
Okay, cool. Thanks.
Now, this is kind of the rather interesting case, which this is something you don't usually think about, which is what happens really when the mixture components becomes quite close. So obviously, asymptotically, we know these models are regular because if you ignore the label switching, but as you saw in the other chart, basically you have two clear components. They're not equal, and the weights are near and nowhere near 0 or 1. But what's really going on here is that because the mixing components are very close, something interesting happening as you see on the small sample regime. You almost see a singular-like posterior. This is why we call these quasi-singular, because kind of it explains what's really going on in these models. So usually you think of them asymptotically as being regular, as you can see on the right-hand side, which is the high sample regime. They're clearly were separated, and they can easily be approximated by quadratic form if you just ignore the label switching. The bottom view, that's just a rotated. I just thought it's a good idea to see the rotated posterior. Obviously, we choose the 2D component Poisson mixture because you can see these charts. Now, this example is going to become quite interesting, but I think this idea that finite sample in a low sample regime, you have some models that are regular but behave like singular because of the posterior geometry. Okay, now this is what happens when you look at them projected. So here I'm showing the rates against each other. So mu0 and mu1. These are just the two rates in the mixture. This is exactly as the same view, but I'm projecting the posterior from the top. Obviously, you cannot see 4 dimensions, so this is the technique to go with that. Now, notice the middle row, that's still the quasi-singular. So you can actually see, as you can expect, air double quote singularity. It's very important to keep in mind that this is actually not a singularity. It's just the posterior is not very clear. If you actually zoom in closely, you're going to see that there's a plane between the two. So the chains are almost going in opposite directions. Or sorry, the posterior is going in opposite direction, and in the middle they're not actually touching. But it's very hard to see it in obviously this projection. So keep that in mind that the projection can be misleading. Now, obviously, the bottom row, that's a truly singular detection routing process. So as you can see here, as we increase the sample size, again, you start to see that concentration of the posterior. Okay, now let's go a little bit into the details. So this is just a quick recap of the free energy. So obviously, this is the definition of the free energy, the negative log evidence, and as obviously as Watanabe showed in the Gray Book and some of the papers from 2000, 2009, this asymptotic expansion, where you have the first term, this is a very typical first term, the likelihood under the true parameter, theta naught, and then you have the RLCT, the second order term, and then you have the multiplicity, and then you have OB1. Now, one challenge with really free energy, just computing it is really hard, as everyone knows. Now, ideally, the asymptotic exemption can be useful for computation, but obviously we need to know the truth. So that's a challenge. We can't actually use it as it is. So we need to lean on some approximation. So the key idea that kind of Watanabe and others have developed is to basically work out the thermodynamic integration, which basically you write down the free energy as a thermodynamic integral over the posterior expectation of different power posteriors. And that kind of gives you some sort of a really interesting estimation mechanics. Now, before we go into the estimation mechanics, just quickly, just to kind of show you why WBSA was driven that way. So obviously, if you take the derivative with respect to the temperature, You get this identity is basically by the mean value theorem that there is a unique temperature such that the free energy equals the thermodynamic integration under a given power posterior inverse temperature. And Watanabe have also showed in 2003 when he worked out WBIC that it has this asymptotic form. You still get the likelihood term under the truth, and then you have the second order term and then the third order term with the singular fluctuation. Now, obviously, for this term to agree with the free energy, we need the temperature to be, or the inverse temperature to be set to some C over log n, and C obviously is chosen to be 1, which is why WBIC uses the asymptotic temperature. Now, this kind of gives us two approximation regimes. There is the tried and true statistical machinery, just use thermodynamic integration and just throw more machines at the problem. So here, obviously, you could compute a numerical integration if you just discretize the temperature interval from 0 to 1 and just basically compute a lot of Markov chain. This is technically the numerical reference for small models. It's obviously quite intractable as the dimension increases, or if you have issues with the numerical integrator itself. Now, opposite to that was obviously WBIC, which is quite fast, and it kind of relies on the first two order term. However, the thermodynamic integration is almost exact if you're able to get the chains to mix well and if you're using a good numerical integrator. But WBIC have been systematically to show some bias, especially for small sample models, for small sample regimes in some models. And that kind of raises the question is how good WBIC can be used for model selection when you have a small sample. This kind of motivated some of the talk, so let's just unpack the bias for a second. So obviously from the expansion here, we can see that there is two important terms. There is the RLCT term, this 1 over beta times lambda, and then we have the singular fluctuation term, which is 1 over root beta times the single fluctuation quantity. Now, MI have already done some work showing that actually WBIC can be adjusted to be asymptotically unbiased, but still kind of raises the question is what really happens at finite-n? Now, the first thing we tried is obviously running this experiment to actually see how can we compare WBIC against some ground truth. So one reason actually we chose the Poisson mixture is we know the RLCT values for all possible nesting. So here we're basically comparing WBIC against the asymptotic free energy, the approximate free energy, but it's not under the MLE, it's under the truth since we know it. So you get this AFE0, which is n times the entropy of the sample plus lambda log n. And since you know lambda, we can actually measure from it. But something interesting you're going to see, WBIC is clearly biased. So just to kind of explain the charts quickly, so the first column, that's the case where we're using the data generating process is two components. This is why it's called M2. It's well separated. This is why it has this separated annotation. And we're comparing kind of the WBIC against the F0 estimates under different models. So we're kind of using two component Poisson mixture or 3 or 5. You can see that as we vary the data generating process, the bias change. And that kind of confirms some of the finding that WBIC is model dependent. It's data generating process dependent. And obviously, as we also vary the model, WBIC changes. The interesting finding here is the bias direction flips. So in the first column, when you're using two-component Poisson mixture model to estimate a two-component data generating process, that's the green box plots. They are in the top right, in the top left-hand side, they are underbiased, and obviously at the bottom chart they are overbiased. And the bottom chart, that's the singular setting. The top right, that's the quasi singular models that I mentioned. And notice that you still get some behavior of the regular model, but as you can see, the bias is quite different. In here, where we only ran 130 simulation, but you can see there is a kind of clear signal that the quasi model behaves a little bit different than the singular model and the regular model, especially for the small sample. Once asymptotic kick in, this is maybe the mid sample size, this 250 tick. You can see that the regular and the quasi are behaving almost the same. Now, this kind of brings up a question. Okay, well, I might have showed that we can kind of adjust for the single fluctuation term by estimating it, but really what we're suspecting is that the RLCT estimation is also playing some factor. So just to remind everybody with the Watanabe RLCT estimator, so obviously because of the identity of the thermodynamic integration and the fact that the way WBIC is defined, You can actually just approximate it by computing an anchor at inverse temperature. So here the anchor is 1 over beta, and you're basically trying to kind of move a small step to compute a finite difference. And you're basically computing two chains. Watanabe have worked a different kind of method that doesn't use two chains, but from numerical simulation, we can see that this is obviously more accurate. So we want to kind of try out what really happens as we vary these hyperparameters. Just keep in mind that there are two hyperparameters here, C and D. C is the base temperature, is where we're deciding to anchor the base temperature, and D is kind of deciding where the step is. Now, Watanabe have already showed that RLCT is consistent. Asymptotically, it will converge to the truth. But that kind of brings a question. Okay, can we make it unbiased? Can we find an optimal parameter such that the estimator is unbiased for different ends? Uh, Sadly, we can't, and this is just because of the way it's defined. Because really, the optimal temperature range, sorry, the optimal hyperparameter range is between the optimal temperature 1 over log n and 0. So you want to really lower D to get close to 0, but what happens is that you're almost dividing by a really high amount, and if you make it really small, you divide by 0. And you can see this exactly in this simulation. So in these simulations, we're computing RLCT, Watanabe's RLCT in a two-component Poisson mixture where the data generating distribution is 2 on 1. And you can see really what happens here when D is small, that's the blue box plots, or when D is actually small relative to C. So even if D is not close to 0, even if it's close to 1, because C is far away, you get this division by 0 issue. And as you can see here, the variance of the estimation is quite bad. It's going negative, which is quite bad for an RLC estimator. Now, I'm just going to take out the high variance estimator just to kind of make you see what's really going on with the good hyperparameters. And you can see here, like, obviously, we're trying to see, can we make the estimator unbiased? As you can see, it's really not possible without increasing the number of samples. The one thing the hyperparameter seems to be doing is changing the variance of the estimator. But obviously, changing the variance by increasing n is much faster because it's 1 over log n. So this is kind of the big takeaway from this chart. Maybe I'll draw attention again to the data generating process. That's the top right of the grid. And as you can see here that the green box plot, this is the ideal temperature. This is the asymptotic temperature. And as you can see, it's quite far from the true RLCT value. Very different behavior than the regular model. But then once asymptotic kick in, you can see that the green box just immediately jumps, which is quite very different from what the singular models behave. So you kind of get this quasi behavior.
So can I just ask about what am I supposed to be, just to clarify what we're supposed to be taking away from the quasi-regular case? So to me, it looks like the quasi-singular case. The quasi-singular case looks like the overall means are like similar-ish to the regular case, which is the top left, but the small n case is higher variance. Is that what I'm?
It's high bias, so that would be
Yeah.
one takeaway.
Yeah.
And obviously, it still behaves somewhat regular, so you can see the direction of the bias. It's under biased compared to the
Yeah.
singular, which is over biased. So the direction is so they're not quite singular, but you can see the high variance here. Yeah, there really should. There really, at least I like to think about it, is that there is a range of samples where the posterior is just not concentrated enough. So any estimates that rely on that sample just diffuse, and that's why you get these high variance kind of like structures.
Yeah. Okay. Thank you.
Yeah. Okay, so now we just look at MI's estimator. So MI kind of used very, very similar. He just kind of looked at the identity for Watanabe, and he basically computed this term, which is using the variance instead of the expectation. One obvious quality of the variance is it's not going to be negative, so we at least know that RLCT is not going to go down. It's gonna if the variance is going to go in the other direction. It has a single hyperparameter, so it's a bit more wieldy to control. Now, more importantly, I might have adjusted the estimator to be able to give you a way to control the variance with something other than the sample size. So this is what's going on here at the bottom left-hand side. You can see that we can actually run multiple chains at the same temperature. but the chains come from different samples, so it's almost like you're computing multiple estimators and taking their mean. And it's as you can see here that there is this nice guarantee that you get this asymptotic normality. The interesting part is you see that the number of chain shows up, so there is a rate of 1 over m, so you can actually control the variance of the estimator by increasing the number of samples. It does have also some interesting properties, but it's still not always unbiased, so you need to kind of do a little bit of work there. So let's just kind of look now at Watanabe versus Imai's estimator. So in this chart, you're going to see we're basically estimating RLCT, both using Imai and Watanabe. We're using the default settings. We're not actually optimizing the hyperparameters just to kind of give the Watanabe a chance. For the regular model, notice at the top left. So just to kind of read the chart, the first column, this is when you're using a model of 2 mixture component. The middle one, that's 3 mixture component, and the right-hand side, that's 5 mixture components. And you're going to see both of them kind of also change their bias as we change the model. Now, the first row, that's the first degenerating process, the degenerating process. That's the regular case, so it's a 2 mixture component, well separated. The middle chart, that's when they are not well separated, and the bottom of the chart, that's when you have a single mixture component, so it's truly singular. The top left, as you can see, both Watanabe and RLCT behaves the same. Variance is not very different. Obviously, we only have 75 samples, so it's very hard to draw the attention. But as you can see, as you increase the number of components, uh, uh, you're going to see that the MI estimator is not doing very well, but that could just be the numerical experiment. The interesting part is k equal 5. You're going to actually see that the MI estimator is becoming quite unbiased compared to the Watanabe, but the Watanabe estimator have this high variance quantity. Now, you can also see the
A-
same.
Sorry, Ash, can I ask a clarifying question?
Go ahead.
So is the data, so in the first two rows, the data generating process is always two components, and then you're just modeling it with like more and more components. Is that right?
We're basically fitting, yeah, we're fitting different models. So in this
So
case,
it's getting like more singular as you go to the k equals 3, k equals 5.
yes.
Okay, okay, thanks.
Yes. And as you go down, obviously the degenerating process is different. So you get different kind of singularity mechanics, but yeah. So I think the interesting part here is this notice the very different behavior between the different DGB processes. The bias also seems to flip, as you can see, that it's under biased in the when it's singular, especially at the bottom. The Watanabe RLCT estimator is quite unbiased when we're using k equal 5. And you can see that it's kind of increasing as we increase the number, as we increase the degeneracy of the degenerating process. So this is kind of confirms that the estimators are subtle, but remember that we haven't yet tuned the MI estimator. So what happens if we tune it? Can we actually control the bias? So MI's work shows that actually we can. So here we are computing different, we're fitting 2 mixture component model with different data generating processes. So at the top row, there we're actually fitting a 3-component Poisson mixture, and the bottom we're using a 5-component Poisson mixture, and we're actually varying for different n. We're varying the hyperparameters to see how the MI estimation does to actually capture the true RLCT value. The dotted red line, that's the true value that we know from the Poisson mixtures. And as you can see that the hyperparameters do actually change the bias behavior of the estimator and also change the variance. From the theory, we know that we can actually improve the individual estimates by just increasing the number of chains and drawing more samples. Here, we're using different samples for every run. But as you can imagine, as you increase the number of as you increase the hyperparameter so the ideal temperature is obviously at 1. That's the true factor because that's the base factor of the temperature. So C equal 1, that's actually the asymptotic value. And if I lower it to 0.1, you can see that the bias changes. And if I increase it, you can see that the variance kind of changes and the bias also does change a little bit. So this should kind of emphasize that we can actually tune the MI estimator to become a bit unbiased. But obviously, this is still a challenge if I'm using a data set where I don't know the data generating process, because you're going to get an estimate and you're going to wonder how good is that estimate. But I think the big takeaway with the MI estimator is that we can address some of the deficiencies in WBIC by basically computing the different RLCT estimator and then computing the SBIC. which kind of relies on RLCT estimates in nested models. We have not done this work here, but we're just kind of trying to show the impact of the estimator and how good it is at capturing the true RLCT value and what kind of mechanics do you really have at small n and as you increase the number of samples. Now, this is so the conjecture when we started the work is to kind of think through, okay, is 1 over log n is the only the temperature should we use? Should we use it all the time? Should we actually find a better alternative? So this is just a heat map showing the root mean square error for the Imai estimator. And you can see that in the top left-hand side, that's the regular case. So we're using a 3-component mixture to estimate sorry, where the data generator process is 2-component, so it's not regular, it's singular. But you can see the red, like the number 1 row, that's the asymptotic theory. He's perfect. He's doing great there. But as you go down, as you increase the number of components, you're going to see that actually the temperature changes, the ideal temperature changes. And you should probably be choosing a different temperature if you want to really capture the true RLCT value. Now, this kind of hinted at what's really going on. Why is changing the temperature plays an important key? So in this chart, you're gonna see. So so I really wish I could point, but basically the level curves here. These are the theoretical Kullback-Leibler curves, and we're basically plotting the level curves. These are quantiles, and we're basically trying to see, okay, where is the Kullback-Leibler level sets? And what's really happening to the estimates. And as you can see, for regular model, you get kind of these nice typical Gaussian ellipsoids. They're quite well separated. So there's no problem there for the estimation, but the geometry quite changes. If we get these components close to each other, they start to kind of interact through the symmetry, and you can start to see this sort of no longer regular-like shape. But what's really happening is that as you increase the number of samples, the samples start to concentrate more around the truth and kind of leave and localize. And because they localize, they become more like Gaussian. That's obviously quite different from the truly singular set because it's a proper, they are full lines. So obviously the posterior have no choice but to kind of concentrate over lines. So this kind of motivates for what really think is happening for these quasi-singular models. And why do we see this quasi-singular behavior for finite samples? Now, the big takeaways here is that in a finite sample, the posterior kind of diffuses and sees more of the parameter space geometry. But as you increase the number of samples, they tend to concentrate more around the singularity and be influenced more from the singularity structure. In addition, obviously, this is the true level sets. For empirical likelihoods, you have a lot of perturbation, and you can see that the interact in an interesting way with like boundaries and symmetries. This is kind of showing the 2D projection. So I'm going to maybe spend a few minutes on this plot. So we're trying to really understand what's really the impact of the temperature. When I increase or lower the temperature, what's happening to my posterior? So here you have you have on the top row, this is we're using a 2 mixture component and we're estimating, and the data generating process is 2 components, so it is regular. There's only label switching, so that's why you see these 2 kind of label switches. The differences between the colors is basically you have what you should expect, as you saw before, is that as you increase the number of samples, they concentrate more. So the way you should really read this chart is that the blue samples, this is from the posterior when the number of samples is small, so they're diffuse. As you increase the number of samples, they concentrate. That's the orange, and as you keep increasing, the more they become more green. Well, now what's happening here is that we try to kind of think through, okay, what would be the equivalent temperature for the different regimes, and we basically we computed the Bauer posteriors to see actually what's happening. In the regular case, not much happening other than the fact that you can see that as you change the temperature, the posterior concentrates. In the quasi-singular, you start to see interaction with the singularity. So as you can see at the bottom left side, you can see that the location of where the concentration is quite different as you increase the number of sample. And that kind of hints that we shouldn't really be thinking of the temperature as increasing information. You can't increase information, you're just emphasizing the data. So what's really happening is that as you change the posterior, they're still heavily influenced by the local geometry of the likelihood function, of the empirical likelihood function. So that kind of explains what's really going on with the estimators. Because of this interaction at small samples, you kind of expect that the estimators should not behave very well at finite samples. Now, more interesting things can happen even in the singularity, in the truly singular cases. So these are two rows where the data generating process is a single component when you're using a two-component Poisson mixture. I draw your attention to the top left. So you're going to see here that as you increase the temperature, you can see that the concentration is not where near the singularity, and this is actually emphasizing the perturbation in the likelihood. Even though, as you can see on the left, on the right-hand side, that as you increase the number of sample, you get this beautiful green crossing. It's nowhere there on the left-hand side, even as you vary the temperature. So that kind of hints that the empirical light, the finite sample regime is rather subtle. There's a lot
Sorry,
going on. The surface can be perturbed. Go ahead, Gil.
can you explain the colors again? Like I know they're different temperatures, but like if when you showed me this plot last time, if I understood it right, like it's like the temperatures are not like green is not the same temperature on the different plots, right?
Yes. So the green here is the equivalent temperature if I have the same number of samples as 5,000. So in this 5,000 chart in the top right chart, this green is actually the true posterior shape. We're basically cooling down the distribution by changing beta, and we're choosing two different temperature regime. One, the orange is equivalent to 250 samples, and the blue is equivalent to 50 samples. So here on the right, the true posterior is the green. And obviously, I keep cooling the distribution to kind of see, okay, how much shape do I get? And you kind of get what you expect from a concentrated posterior. They are tracing out the Kullback-Leibler level sets. While the 250 is still the green, is if I raise the temperature to match the 5,000 samples, but you don't get quite the singularity. And it doesn't matter how many chains you run, the singularities is still not as quite clear as it is in the 5,000 regime. And obviously in the 50 range, the likelihood is quite perturbed. Uh, I think the one that was interesting, see, I'm trying to see if I could exit this. Get this better. So you can see at the bottom left the chart, as you increase the temperature, actually the green is almost at the boundary. And this is just kind of hinting that there is some interesting things happening at the boundary. Now, obviously, as you draw different posteriors, you get different geometries. But I think this is kind of we're trying to really to understand what does the temperature do? Why is 1 over log n? What's really the recommendation there for an obliged statistician to deal with 1 over log n? And clearly there's a lot more work to do. So what did we let's kind of wrap up.
Would you mind just explaining? I'm still a little confused about the how the temperature is being set here. So is it that you're taking the n equals 5,000 and you're looking at for the inverse temperature set to 1 on log 5,000, you're setting the temperature in the two plots on the left-hand side, the two columns on the left, so that n times beta is equal to 5,000 on log 5,000, or
Yeah, I'm basically I'm kind of solving an equation where I'm basically saying if I wanted the same temperature as 1 over log 5,000, what should that be when I have 50 samples? And
yeah.
that is giving me the temperature drawing out the green.
So you're treating n beta as the temperature, like
Yeah.
including n in that. Yeah, okay. Yeah, cool. Thanks.
The idea here is just kind of we wanted to see, okay, what does really the temperature do in the finite sample regime? Obviously, when you have a lot of samples, the effective temperature is just tracing out the theoretical level sets. Okay, so this just kind of concludes what we've talked about. So just kind of the big takeaways. WBIC is biased and is model and data generated process dependent. For a small n, WBIC estimates can be unreliable, especially when we're doing model selection. Quasi-singular models, they are regular asymptotically, but they behave or they have a singular-like geometry at finite-n. Watanabe RLCT estimator is inherently biased. The only ways you need to either correct it by estimating the singular fluctuation or applying other techniques. The Imai estimator is a bit more robust and obviously enables other free energy approximation by using techniques similar to SBIC. Beta equal 1 over log n is not really, that's a great asymptotic relation, but there's still a bit more work to be done for finite samples.